Hi students, I have good news. Today is the last lesson of the acid-base unit. So just to take a look at the test outline, okay, remember our test outline? This is the last topic and it's called Bronsted-Lowery acid-base theory. And it's really easy and I don't want to leave it out because it really does bring the acid-base chemistry to the expansion of beyond the Arrhenius theory. Let's just reflect back. Arrhenius said acid yields H plus, hydrogen ion or hydronium ion. Base yields OH minus, which is hydroxide ion. So this whole time we've been looking at H plus, OH minus, coming together, making HOH, which is water, which is neutralization. Now, Bronsted-Lowery comes along and they expanded the acid-base theory into no longer just H plus, no longer just OH minus, but really more about proton transfer. It all came down to H plus or proton transfer. And if the proton is going to be transferred, then the definition of acid is a proton donor, a species that gives up, and the definition of base is a proton acceptor. So acid is a proton donor, base is a proton acceptor. This is an alternative theory to acid-base chemistry. It's an alternative theory. We're now expanding the theory to not just be limited to hydrogen ion and hydroxide. Now we're looking at the movement of the proton. So this is a very simple concept. I'm going to show you kind of the trick way of identifying the acid-base pairs. They're called Bronsted-Lowery conjugate acid-base pairs. So we're going to look at the paper exclusively and see how this works out. All right, so we're going to start with H3O plus, which is hydronium, plus HSO4 minus, in equilibrium with, so we're going to assume these are going back and forth, H2SO4 plus H2O. So if we look at a chemical equation like that, basically step one is to link the similar pairs across the arrow. So it's very easy to do. Do you see how H3O and H2O are similar pairs? They differ by one hydrogen ion. So I'm going to link them. Do you see how HSO4 minus and H2SO4, they're similar across the arrow? They differ by one H. So I'm going to link them. Out of the pair, the species with the most H's is the acid linked to the base. Out of the pair, the species with the most H's is the acid linked to the conjugate base. The rules are always the same. Acid is a proton donor. If you look at it as a cycle with the two reactants, acid is a proton donor giving that H plus to the HSO4. So this is the acid and the HSO4 is the base. H2 is formed. H2SO4 is formed. So we can look at it as a cycle between the two reactants in the forward, or we can link them and find the acid-base conjugate pair. I like linking them because by linking them, you can do any question. So let's try another one. H2SO4, which is sulfuric acid, plus OH minus, SO4 minus 2 plus H2O. Link the similar pairs across the arrow. This is an H2SO4. This is just SO4. So, OH, H2O. And I think I left out an H here. H2SO4, HSO4. Out of the pair, which species has the most H's? Acid, conjugate base. Out of the pair, which species has the most H's? Acid, base. Acid is the proton donor, base is the proton acceptor. Acid is the proton donor, base is the proton acceptor. Acid-base conjugate pair, write that down. So this is an acid-base conjugate pair. And they differ by 1 H. So look at the expansion of this theory. Look at this. Water acting as an acid, water acting as a base. It was unheard of. It wasn't what Arrhenius had said. So look, we have water acting as both an acid and a base. So when we have a substance that can do that, it's called amphoteric. Like an amphibian can live on both land and water, amphoteric means that the substance has the ability to act as an acid or base. So it can be a proton donor or it can be a proton acceptor. So amphoteric is that phrase that we use to describe a species that can act as both an acid and a base. It's also called amphiprotic. I've seen that word also, that it can both act as an acid or a base. So just to give Bronsted, Lowery their due, that is the alternative theory where an acid is a proton donor and a base is a proton acceptor. So now we have been able to expand acid-base chemistry to talk about something different, something expanded in terms of how acids and bases behave. And that finishes the unit of acids and bases.